It's increasing and it's
I think I don't think we're gonna get through everything I had planned on getting through. So we'll probably knock off at least the last section of the homeworks, the last two problems. I'm gonna try to get through at least some chunk of 6.5. So there's, you might have to do a little bit of reading for that section, but I'll reorganize the page to adjust. Okay, so today we are going to finish. So last time we talked about discrete subgroups of R. I'm going to spend a little bit more time today talking about discrete subgroups of R, but also of R2. And well, I mean, this kind of thing applies for Rn too, but say a little bit about that. Okay. So I think I got to a point where I just didn't have time, and I had was trying to prove a statement. And let me see if I can't do that now. Okay. So the lemma is as follows. Let gamma be a discrete subgroup of R. Subgroup. Remember, that just means that the points are sort of isolated, they're separated from each other. And the addition operation is used in our. Then either gamma 0 or gamma is equal to Z times R for some. Well, here we can say take R positive. It could be anything non-negative. Zero case. So the proof is basically like the one we did for abelian for Z, except it's a little different. We don't use the division algorithm, but we sort of do find a minimum of something and then show that everything is generated by that same. So how do we do it? Well, recall, I think we did get to the point where we talked about the least upper. As I said, first take epsilon so that gamma intersect the interval around 0 is just above radius epsilon. Got some region around the origin that does this because, again, it's discrete. So, and then define R to equal the greatest lower bound of epsilon infinity intersect. So we got some collection. So here's the picture. Here's 0. And we have a bunch of points. A priori, we don't know where they are in R. These are in gamma. All these points are in gamma. And then since we know it's discrete, we can find a little neighborhood, around 0 that's completely away from all the other points except 0 in gamma. scan. All right. So now we can take this region, and take it all the points in that region. So we've got a bunch of points in gamma in this region, and we're just going to take, I'd like to say the smallest, but maybe I can't say the smallest. And if I had just an arbitrary set, I'll just take the least upper, maybe it's some accumulation point. Anyway, there is such a point. This is by the axioms, the completeness axiom of the reals. Okay. So, claim that I didn't prove last time. So R is in. Someone can tell me, I think, why is that true? M is equal to, I'm sorry, say it a little loud. We're trying to prove the lemma. We're trying to prove the lemma. Yeah, yeah.
Isn't what you're saying with the R equals greatest lower bound is that R just is the smallest number bigger than 0 that's in gamma?
Nope. No, if I, for example, so this is just, if I take greatest lower bound of 3 to 17, the open interval, this is equal to 3. It's the largest bound thing that's below all of those things. But 3 is not in the open interval 3 to 17. Right? So greatest lower bounds don't have to be, in the sets that they're bound. If I take an open interval and take the greatest lower bound, it won't be. It's just the biggest possible bound that you can have. So this is not, so we want to say what you want. We want to say it isn't. Is it clear what we wanted? So how do we do it? If it's not in there, what do we know? We know that we've got a sequence sort of getting closer and closer to it. Right? We definitely know that. Because if we didn't, if everything stayed, far enough away from it, we could have a larger bound. Right?
Yeah. If R was 0, then we know R can't be 0 because R isn't in epsilon to infinity, but 0 would be the only element of gamma smaller than R.
Right. That's right. Right. So so if you look at this region here, since we're taking the blue region, right, we know that the greatest lower bound will at least be epsilon, right? Because anything over here, we can get a larger number, that would be a lower bound. So it's going to at least be epsilon, which means it's definitely not 0. 0 is not going to be the one that we have. That's sort of why we wanted to get this epsilon, is to kind of move away from 0 in a sense. Well, let's say, so suppose it's not, suppose not. I claim there are at least 2 elements, say R1, R2, in gamma, intersect this positive, this big, such that, well, R is it's the greatest lower bound, but it's a lower bound. So R is less than R1, and that's less than R2, and this is less than R1 plus. Sorry, R plus epsilon. So over here, so let's see here. In other words, let me take this picture. Let me magnify it a little bit. So what I'm saying is the following. I'm saying, okay, let's say I have my green is my greatest lower bound here. Okay. Well, and the red points are points in gamma. Okay. That means, well, if this were a picture, then I could get a bigger green. I could kind of move the green up a little bit, and it would still be a lower bound for all the red points. So what has to happen is I have to have kind of an infinite sequence of red points getting closer and closer to the green point. It would still be a lower bound. So what I'm saying is if I take this epsilon neighborhood around the green, which is, or I just go up by epsilon, then there have to be at least 2 points in there. So why do I want at least 2 points? This means I can take R2 minus R1. And since R2 minus R1 is, since R1 is less than R2, this is strictly greater than 0. And since they're, both in an interval of the size epsilon, their difference is going to be less than epsilon. So what's wrong with this? So what?
It breaks our definition of discrete subgroup. Contradicts it.
It contradicts something. What part? I mean, I don't want to say you're wrong.
R minus epsilon, R plus epsilon in gamma, you only can have R.
Right, exactly. Well, not R minus. Yeah, it's not R. It's more this.
Well, for any, like I'm talking about when we wrote the definition last class, like for any R in gamma, for any element.
Okay.
In that epsilon neighborhood around it, you can only have R.
I think that's a fair statement. Let me go resort to what I've written here today. So what we have here today is we chose this epsilon so that this intersection just contained 0, right? There were no other elements of gamma in here, but we just found one. This one. It's between 0 and epsilon, so it has to be. And this is remember, these two guys are in gamma. Gamma is a group, so minus R1 is in that group. We can add things in that group. So this. All right, so this would be a contradiction. And so R is in gamma. So that means we have a picture here. The picture is just that if we look at 0, there's this element R, and there's nothing else between 0 and R in gamma. All the other stuff is to the right of R. So then the next claim is that indeed gamma itself is equal to Z times R. And the proof of that is not hard. So suppose I don't know, let's say R tilde is not, it's in gamma, and R tilde is not in the R. But then R tilde has to be between AR and A plus 1 times R for some A. Maybe we'll, okay, so here I guess I want to assume that R tilde is greater than 0. So this, if R tilde is not greater than 0, take negative of it, make it positive. I mean, this would be true, right? So actually, this is just right, because I mean, we can break, all I'm saying is if I break up my real line, I've got, into these intervals, well, this guy has to be in some interval. All right, but then if I subtract AR, I get 0 is between AR and R. This is an element of GAM, again. But we just said R is that element, is the sort of uniquely defined element, so that nothing is in GAM is between 0 and R. So this is a contradiction. Definition of R. Or maybe the previous claim. So that's it. That's the proof of the lemma. That says that gamma is equal to D times R. So we'll use this lemma again a little bit later to look at discrete subgroups of R2. And indeed, there's kind of a general thing I'll mention in a minute. Okay, so why do we want this for now? Why do we want this this lemma? We were after the following theorem, namely to describe discrete subgroups of, or finite subgroups of O2. So we were interested in finite subgroups of O2. Orthogonal group. And we claimed that they're either CN or the dihedral group. These are the only two possible possibilities. Sort of linear symmetries of the plane. It's a quick dihedral. Okay, so how do we prove this? So we want to use this lemma that we just used. So, well, we can do the following things. So it's a kind of, I'm really tempted to do something that I guess you'll like it. Well, anyway, so there's a homomorphism. From R plus to O2. Which just call it V. What does it do? It just says phi of theta equals rho theta. It says rotate by theta. So you can, this is a homomorphism. I rotate twice, by theta 1, theta 2, I'm rotating by theta 1 plus. Now, what is the kernel, by the way? Don't tell me. Remember what a kernel is?
2 pi times n.
2 pi times n, right? 2 pi times, I'll just say 2 pi times a. I'll use a because I want to use n in a minute. So I got these n's up here. 2 pi times a, where a is any integer. If I rotate by 360 degrees a times, I'm still not doing anything. Even if I rotate counterclockwise, it's a negative a. This gives me a homomorphism. And now I can take my discrete subgroup. I'm looking at it as a subgroup of O2. So I can take my, I can take my discrete subgroup. So consider my finite subgroup. Consider the inverse G. Remember this, we defined this a while ago. This is the set of all elements, in this case in R. So I'll say SR. So when I look at the image of S, this is an element of G. Remember, this is just rotating by S. This is a subgroup of R. Addition. Now this has got to be a discrete subgroup. This is discrete. Why is that true? I think I have a picture in their brain of this thing. They're like a picture. Let's just share their picture of this. Very Kayla's going. That's right. That's right. Good picture. I agree. Here's R. This is actually really, I was tempted to call it this, but I didn't want this. This is the exponential. Essentially, but maybe. So here we've got, so if I just think of the rotations, SO, right? I got a circle. This is SO, SO2. That's what this is. It's all rotation. And I take this guy and I map it to here. And the way you can kind of think about it is you can think about, you know, like just projecting. Take a big spring. And I mean, you're just saying, okay, look, if I rotate by 0, I don't do anything. If I rotate by A, I start rotating. And then once I rotate by 2 pi, I'm back to, I've gone all the way around. I don't do anything. I rotate by 4 pi, I don't do anything. That's the picture. So if I have a discrete subgroup, which I'm saying I do inside of, well, it's inside of O2, but I'm looking at the part that's in SO2. I have some discrete subgroup, and I look at the inverse image. Well, it's going to take that discrete subgroup, and then it's just going to repeat it. It's going to take that block, and it's going to repeat it over and over again. That's the inverse image. All the things sent to it will just be kind of, you can sort of draw a line through your spring, and these are all the points that are mapping to this point. So if it's finite downstairs, it will be, you'll be able to separate the points upstairs. Be able to separate them by little, by the same intervals you can get on the circle. Does it make sense? Questions? So what I'm saying is, so I want you to note this. I don't want to prove this anymore. You can look in the book if there's, you know, this is just follows from the fact that this is sort of locally one-to-one. But I don't want to say any more about it. But now, assuming that we believe this, so we have a lemma that says what this is. So in particular, phi inverse of G, it's a subgroup of R plus, it's going to be Z times some number R. Right. We also know something else about this. We know that the kernel is contained in it because if the kernel goes to 1, it's in this group. So in particular, this also has the element 2 pi. But that means that 2 pi is a multiple of R, an integral multiple of R. some integer times r. R is positive. So we can say 2 pi, now we'll use our n. That's equal to r. But sorry, this 2 pi is equal to r times, where r is equal to 2 pi over. And once we know that, well, we know everything else in the inverse of G is a multiple of 2 pi over n. So that means that everything in G itself is going to be rho sub some multiple of 2 pi over n. So it's going to be a rotation, which is rotates the angle of 2 pi over n a multiple. So G, just write down what I just said, 2 pi k over n. K, here we can restrict, but once we get to n, we know it's the identity. So here, k can be greater than 0, less than n. This is isomorphic to C. The cyclic group of order. So what we've shown is that if we look at the part of G that preserves orientation, it must be a cyclic group of order. So you'll notice that I only talked about SO2 here rather than O2. I said I have a discrete subgroup O2. And actually, I'm sorry, I should say this G is rather phi of the inverse of G. And this part of G is equal to G intersect SO2. So in other words, this is the only, if I take the inverse image of the ones that are reversing orientation under this map, well, they're not in the image of that map, so there is no pre-image. There are no elements going to this. Okay. So what we want to do, so certainly what we've shown so far is if G is only consisting of orientation preserving isometries or orthogonal isometries, then it's cyclic. So now let's suppose G contains a reflection. Well, we can change coordinates for G. So we could assume, it's a container reflection about some line. We can, G is just in O2. We haven't set a coordinate system. So we might as well just rotate our coordinates so that that line is the x-axis. So we can assume after changing coordinates, which is just a conjugation, this reflection is R naught. That's R. Now I regret using R. Okay, well, R is gone because it's 2 pi over. This is the R that looks like this. Well, we know but then we know we know that G will contain the dihedral group. So that then since dn is equal to, is generated by, let me write it this way instead of writing it out, generated by R and 2 pi, a rho of 2 pi of n. We have a dn contained in G. So all of these guys, because this R and our rotation will generate, as we saw last time, will generate the dihedral group. So how come we don't have anything else in it? Well, the reason is if we had anything else, we could multiply by R and get another element that's orientation preserving. And we know what that is. So in other words, if R tilde is any other reflection, or, yeah, I'll just say, in other words, it's in G, but not in Tn. R tilde is in G, R tilde is not G in Dn. But then, well, if we hit a reflection with another reflection, we're back to where we started. R times R tilde is an element of G. I mean, they're both in G, so this is, but it's also an element of of SO too, because two reflections will give us something orientation preserved. But this we know is Cn. So because we know what that is, we can say this is equal to, and I'm multiplying by R on the left, we get R tilde is equal to R 2 pi k over n, which is an element of P. So that would be a contract. Is that it was not? Okay. So that's it. That proves that we can classify our finite subgroups of O2. Now, what is done, I don't think we're going to do it. Pretty sure we're not going to do it. Is you can do this, run this kind of classification for O3 as well. Very famous. And the Greeks knew about this. Yes, go ahead.
Does K have to be an integer?
K is an integer, yes. Okay, yes, sorry, thank you. That's just an integer. That's not, that would be pretty much anything you want. So I was to say that you can do a similar kind of a thing for finite groups of SO3 or O3, and this is quite a nice and famous kind of classification of groups. These groups are very useful in all kinds of contexts in mathematics and in physics and in chemistry and all of that. They describe sort of crystals and crystallographic. We'll do some of that with the plane. Next. So before I get to that, I just wanted to mention something, which is maybe a little bit of an explanation of this map here. So there's another way, there's a group that's isomorphic to SO2, or sorry, the orientation preserving part of M. So we consider, I'll just call it M. I don't remember if the book has a notation for this. So we have this subgroup of isometries of the plane that preserve orientation. There's another group we can actually write down that is isomorphic to this, which is a very simple group, very easy to understand group. So this is isomorphic to the group of sort of linear like transformations of complex planes. So I'll just call it, I don't know what to call it. What?
Doesn't that say like M to the
or for orientation? Yeah, sorry, that comes from other kinds of, or this is used in very specialized areas. Anyway, so here we can consider all the following things. We can look at e to the I theta z plus, let's call it alpha. If theta is in R, alpha is in C. And this is think of this is a function, a linear function, or an affine function of, so take z An operation here is composition. And the point is that you can isolate your translations and rotations. This is the oops. This part is a rotation by theta, and this adding alpha, where alpha is an element of C, which you can think of as the plane, the real plane. You can, this alpha will translate your space. This is sort of the most elementary, well, not the most elementary, but one of the most elementary of what are known as linear fractional transformations of it. Form a larger group, and one that sort of acts on the sphere. Extended. So anyway, this isn't an Artin, but I thought it was worth mentioning. If you study complex numbers or take a course on complex analysis, I'm sure you'll run into linear fractional transformations. And our study of isometries is a sort of a small subgroup of that larger. And that group does less, strictly less, than our isometry group. So our isometry group wants to preserve the rigid geometry distances in the plane. So we want to hit the plane with some map that preserves all the distances. That group of linear fractional transformations rather takes the plane and wraps it into a sphere, and it considers all possible maps of the sphere that preserve angles, so-called conformal maps. So that's also a very interesting group, and still kind of finite dimensional and understandable. There's a beautiful video by some mathematician in Minnesota. A little pretentious. I mean, some music in the background and stuff. Kind of like shows the various ways of this group sphere. Like movie night or something. All right. So now what do we want to do? So now what we would like to do is we would like to kind of think about M for a moment and prove a result about M. So M, want to show, and this is, let's see the name of the theorem. Okay, there's a theorem that says any finite subgroup of M is isomorphic Cn. In particular, it is going to be a collection of if it's Cn, it's going to be a collection of rotations about some point in the plane. Some point in the plane. If it's Dn, it will be those rotations about that point and some reflections about lines through that point. That's a little surprising. I mean, I think you could think, well, okay, I could just kind of do something different and get a finite subgroup, but no, you can't. Try to do something different, try to add sort of a translation component, you'll end up getting an infinite group. And we'll study those in a minute. So what's the proof of this? Well, the proof follows from a fact that that M is consists of what are called affine transformations. So elements of M, isometries, I'll just say this, isometries are affine transformations. And what that means, it doesn't mean so affine is sort of a looser version of linear. It's not quite linear. They're not linear because the translation is not linear. But there is some sense in which they preserve the algebra. of the plane. So what does this mean? It means if I have vectors v1 through v2, vn, maybe I should choose vm. These are vectors. So they're in R2. Vectors. You don't have to think of them in R2. You can think of them in, well, let's set it R2. And we have numbers, alpha 1, alpha m, are satisfying a single constraint. Such that sum of alpha 1 is alpha m 1. And then an affine transformation, or let's say T, I don't want to call it T, let's call it S. R2, it's affine. If I look at the linear combination with these coefficients, any coefficients like this that satisfy this constraint, this is equal to the same kind of linear combination, but with the values of S. It's called an affine transformation. And what it does is it says, you know, if I think of the plane, there is a notion of sort of betweenness, there's a notion of arithmetic, but I don't really have a notion of zero, of the origin. So I can sort of, if I have 3 points in the plane, for example, I can make a triangle, right? Connecting those points, right? And that's something I can do. Those are going to be sort of affine transformations, but I don't know where zero, I don't care where zero is to make a triangle. So if I have an affine transformation to preserve that operation, these types of linear combinations are sort of like drawing line. Let's say you take 2 points in the plane and you consider all of the affine linear combinations such that alpha 1 plus alpha 2 equals 1. What you get there is you get the line between those 2 points. Okay. So you want, isometry should preserve lines. And so this is sort of a natural thing. So why is this true? So this is true. So this true. Well, if it's orthogonal, it's linear. So this is definitely true for if S is orthogonal. So the only thing you really need to check is translation. Okay. Let's say I take translation of this thing. Alpha 1 V1 plus alpha M VM. Well, this is equal to, I just take alpha 1 V1. It's alpha M VM plus V. Right, that's the definition of translation. I just add V. Okay. But V is also known as someone's going to catch on to this technique of mathematicians of not doing anything, right? V is also 1 times V. V is 1 times V. What's 1 times V? Well, 1 is the sum of the alphas. Equals alpha 1 of V1 plus V. It's reorganizing using the distributive property or linearity if you want. B. Great. So this is an affine transformation. Isometries are affine. And now why do we use that? Or why is that important? Well, there's some, so Artin doesn't talk about affine transformations, but he does prove something in the section where he says an isometry will take a centroid to a centroid. And the centroid is sort of your center of balance. So if you think of each of the points as being sort of equally weighted, it's sort of the center of balance of all of the points. You're building, what do you call those? Mobiles. You guys ever have the fortune of having, or if you like mobiles, for some weird reason. So what am I doing? All right, so this implies, so what is the centroid? Centroid, I don't really care what a centroid is, but okay, here's a centroid of say vectors. Again, we'll just say v1 through vm. It's just 1 over m times v1. It's sort of the average. It's sort of equally weighted. So what you can see is you can see that this will be preserved because of affine, of the affine property. Okay. So, but this is sort of parenthetical. We can do without it. Instead, what I want to do is the following thing. I want to say, which is basically this argument, but I want to say the following. Okay, so what are we trying to prove? I'm sorry, I lost my train of thought there. Well, I want to prove that any finite subgroup of M is of this type. And in particular, that its rotation is either Cn rotating around a particular point or Dn around a particular point. And so in order to do that, what I'm going to do is I'll take an arbitrary point and I'll consider what's called its orbit. So suppose G is finite now inside of M. Take and let B be any element of R2. So then consider following element, namely, let's call it W, equaling sum 1 over G times the sum G and G of G times G. So I mentioned centroids a second ago, but this is sort of the centroid of all of these elements G, because I've got G elements. Well, what is the point? So, well, this is, I guess what I want to say is this is an affine combination because there are precisely G elements, right? There's one element for each G, and the coefficients then are all 1 over the order G. If I add all the coefficients up, I get 1. I get G, the order G times 1 over the order G. This is an affine combination. Then what I want to say is if I hit this with G, what do I get? Well, because I get G of this, but I know that affine combinations, sorry, let me call it G tilde. I know that affine combinations are sent to affine combinations. So this is 1 over G as a sum of G tilde, G. But here I'm multiplying each of the elements of G by G tilde. G is a group. So this is just multiplying by G tilde will just permute all the elements of G around. So these are all, I mean, they're different elements of G, but as I span through each element of G, multiplying by G tilde on the left will give me each element of G, just in some different order. Invertible thing. So this is also equal to W. This means W is fixed by all elements. But we know we've classified the elements of M. There are either rotations, right? They're rotations about some point, right? Or the identity. They're translations. Translations don't fix it. Right? If I translate, nothing is fixed by translation. So these are definitely not translations. So they're going to be rotations or reflections. Glide reflections will not fix it. Reflecting and then gliding. So these are going to be rotations or reflections about some point. And it has to be the same point, namely W, because that's the point that's fixed. So that means after a change of coordinates, you get a finite subgroup of O2. So these are all fixing that point. If you change coordinates to that point 0, these are all going to preserve 0. And that verbally concludes the proof. Sorry. So I didn't even get to 6.5, which is very sad. And I apologize deeply to you all. So don't do any problems from 6.5 or 6.6 unless you want, which leaves about 3 problems, I think. So the review session might be very helpful. I will make the adjustments this afternoon to the homeworks, but I anticipate everyone will do very well on this one. I'm going to try to get a take-home midterm early next week. I don't know about Monday, but early next week, I'll give it to you. You'll have a week or so to do it.